This is Ritesh Srinivasan and welcome to my channel. In this video, let's look at an interesting research paper termed as Designing BERT for Convolutional Networks, Sparse and Hierarchical Modeling, or SparK masked modeling. Okay, so they claim here that this paper, the technique used in this paper is the first successful BERT-style pre-training on any convolutional neural networks. Okay. So in BERT, you have something called as masked language modeling for pre-training. Okay, where when you have a set of words in a sentence, certain words are masked, and then the BERT transformer model is pre-trained to identify that particular word. Okay, to kind of generate that word, right? So that is masked language modeling. Now, how do you extend that to images? Okay, for say convolutional neural networks. So what they say over here is that in case of your vision image transformers, an input images is divided into several non-overlapping patches. Okay, simply dropping masked patches or replacing them with masked tokens can remove the information, but for a transformer it is able to handle irregular or variable length and non-overlapping patches. Okay, so it can work for transformer models. But in convolutional neural networks, removing the information of masked words is difficult. Okay, so in a convolution neural network, if you don't have this, because you cannot have this non-overlapping patches, right? Because convolutional neural network cannot operate; they only operate on regular grids. They also perform sliding window with overlapping. So if you zero out all masked pixels and feed this mosaic into a convnet, this can lead to issues like data distribution shift, okay, and other issues. Okay, so this cannot be a solution over here. Okay, why you cannot extend your simple masked language modeling to images? Okay, so this is one issue with your what you call convolution neural network, because there you have this convolution operation itself is like it operates on regular grids, and there is this sliding window with overlapping. Okay, and another thing is that single scale algorithm cannot learn multi-scale features. Okay, so in image computer vision, you have these multi-scale features and pyramid networks. Okay, whereas masked language modeling is more or less a single scale manner. So you cannot use it directly on convolutional neural networks. So these are two restrictions why you cannot bring this, masked image modeling on convolutional neural networks. Okay, so how did they overcome these two disadvantages, or these two technique issues which are not suitable for convolutional neural networks? So what they are saying is that they introduce something called sparse masked modeling with hierarchy. Okay, that is a SparK. So first it randomly masks images in a patchwise manner. Okay, observing the sparse nature of point clouds coincides with these unmasked patches, so they treat them as a flattened 3D point cloud and then use something called sparse convolution for encoding. Okay, so because of this strategy, the information of eliminates the information of masked parts by avoiding convnets to easily handle irregular masked images. Okay, and then for decoding, they will fill empty positions on multi-scale features with mask embeddings and feed them into a multi-scale decoder. Okay, so this is their technique over here, and they say that this shows improvements on outperform state-of-art contrastive learning and transformer-based mask modeling by large margins. Okay, so they say the improvement over COCO baselines are more significant as an ImageNet, indicating that these representations are highly transferable. Okay, so in summary, what is it actually? It is a technique. What they have done over here is that you have an input image. Okay, you mask certain regions of the image, then they have something called as sparse gathering to convert it into some kind of a 3D representation, on which they do something called sparse convolution. Okay, which through which they do hierarchical encoding over here, and they also have hierarchical decoding to reconstruct the image. Okay, so once this network is pre-trained in this particular fashion, okay, what happens is that you can then use only the encoder part for your downstream tasks, just like your BERT. Okay, in BERT you do some pre-training on language, on your text, and then you try to use the encoder representations but embeddings for downstream tasks. Similar technique over here. Okay. So what they say is that to adapt convolution to irregular masked input, visible patches, okay, in the image are gathered into sparse image and encoded by sparse convolution. Then to pre-train a hierarchical encoder, they employ unit style architecture to decode these multi-scale sparse feature maps, okay, where all empty positions are filled with mask embedding. So that is this densifying thing is necessary to reconstruct a dense image. Okay, in this way they can actually train a particular pre-train a image, what you call, for generating image embeddings, okay, or features basically, right? So this is again explanation of why that transformer based masked modeling cannot be used over here. Okay, so to overcome this ensures they do sparse convolutions. Okay, now what is this sparse convolution at a very high level? They explain it in this particular figure over here, right? So if you have a binary mask like this, okay, raw mask binary where you have these dark areas are unmasked and the white areas are masked over here, and if you apply your normal convolution operation, what is seen is that by repeatedly applying the convolution, your mask information is lost over here, right? It causes dilation and there is loss of this mask information, right? So what they say is that as when computing ordinary dense convolution centered at 0, which is the masked positions, the result would be non-zero if the filter covers any non-zero unmasked points. Repeating this convolution will erode the masked regions and dilate the unmasked ones, okay, leading to the vanishing problem. So what they do is that they make use of sparse convolution, whereby what happens is that it will only do convolution on the unmasked regions, okay, by skipping all masked positions and keeping the mask pattern as such. So this retains the mask pattern. So they make use of something called as sparse convolution, which is explained in this particular paper called Submanifold Sparse Convolutional Networks. I'll be putting the link of this paper in the description of the video. You can check out that. Okay, they also have a PyTorch library for this particular sparse convolutions. Okay, so that is the idea over here. For the decoder part, they use unit. Okay, so that is this particular part where you have the decoder, and in these features wherever mask is present, okay, what they do over here is that where is that part? Okay, decoder, they do something called as densifying to fill in all empty positions on sparse feature maps, okay, are filled with mask embedding to get a dense feature. Okay, then they do the decoder. That is what it is. And after pre-training, you can have a head module, so which can have 2 or more upsampling layers to reach the original resolution, and then you can do your downstream tasks. Okay, so that is the idea over here at a very high level, and they say that this is actually improved the results on compared to your what you call transformer based or contrastive learning based downstream tasks, okay, compared to those networks. They show over here some improvements. Okay, let us look at some of the reconstruction results to check how the model performs in pre-training. Okay, so what they say over here is that this is the original image, this is the masked input, this is with a mask ratio of 60%. Okay, so this is prediction plus input. Okay, so without unmasked patches copied from raw input. Okay, so the unmasked matches have been copied from raw input over here. So this is the prediction. If you look at the pure prediction, this is how the image looks like. Okay, this region is highlighted over here. Okay, zero out all unmasked patches. So when you do that, this is the patch which has been predicted over here in the masked input. Okay, so it does some decent prediction over here. Maybe we'll zoom in a little bit. Okay, yeah, so it does some decent prediction of this particular region. Okay, This is another image where you have this masked input, right? This is the prediction plus input. So what is that? Some this region is predicted plus the original input is what is shown over here. This is how the raw input looks like. Okay, this is by zeroing out all unmasked patches. This is what has been reconstructed. Okay, so what they are saying is that in the particular columns, the round shape of red fruits from very small portion of exposed edges can almost reconstruct. Okay, some clear texture has been reconstructed. Okay, so the texture has been reconstructed in some of these, in this particular image, in the third column. Say, because the texture has been reconstructed, it can capture the visual signals properly. That is what is written over here. Model can capture the visual signals with medium or high frequencies. Okay, the model can almost reconstruct round shape of red fruits. Basically, it can almost reconstruct the round shape over here. Okay, over here as well, right? That is what they say over here. So the model is able to make different but plausible predictions on masked regions. Okay, that's what they see over here, how well it predicts the masked regions. Okay, so I hope this short video on SparK, which is about sparse modeling, okay, sparse masked modeling on images, is useful for you. So if you like this video on this particular framework, please like, share, subscribe to the channel. I'll be putting the link of this paper along with the GitHub link, okay, along with the link for the paper on sparse convolution networks in the description of the video. You can check it out. See you in another video.